Hello everyone, welcome. Today we'll be reviewing chemical equilibrium, reaction rates, and Le Chatelier's principle. I'll be emphasizing on what exactly is important to know for your TEAS exam, and we'll be finishing off with a few practice problems from the official ATI TEAS study guide. Let's go ahead and get started. We know in a chemical reaction there is a reactant side and a product side. Many chemical reactions are reversible, meaning the chemical reaction proceeds in both directions, and this is indicated by the double arrow. Your reactant forming a product is called the forward reaction, and the product reversing and forming the reactant is called your reverse reaction. In a chemical equilibrium, the rate of the forward reaction is equal to the rate of the reverse reaction. Also, the ratio of products and reactants is constant, meaning the amount of reactant and product does not change, it stays the same. Chemical equilibrium is kind of like a seesaw effect, where you have reactants on one side and products on another. If the reactants dip too low, the system will make a change as to keep the reactants and products even again. And if the products dip too low or go too high, then the system is again going to try and make the reactant and product balance again. Lastly, the forward and reverse reaction never stop moving. They continuously move in order to keep the balance of equilibrium. So a system that is at equilibrium never goes into completion. It keeps working and keeps moving. You can see in the visual here, the forward reaction is moving towards the product. At this very same time, the reverse reaction is moving towards the reactants. Le Chatelier's principle states that if an external stress is applied to a system at equilibrium, the system will adjust to reestablish in order to maintain equilibrium. By the way, system refers to the reactant and product as a whole. Factors or stressors, as we call them, that affect equilibrium are heat, pressure and volume, and concentration. If we add stress to a system, there will be some type of system adjustment made in order to bring it back to equilibrium. For example, if generally we increase the heat, the system will lower the heat. If we increase the pressure by decreasing the volume, the system will try to decrease the pressure by increasing the volume. And if we increase the concentration of one side of the system, it will try to decrease the concentration. Basically, according to Le Chatelier's principle, whatever stress is done to the system, it will try to undo it. This creates a nicely balanced system. And what are we balancing exactly? We're balancing the concentration of product on one side and reactants on another. Now that we have a general idea of Le Chatelier's principle, let's look at a generic chemical equation and apply Le Chatelier's principle to it. It is always important to make note of what state the substances are in. Here we have A as a solid, B as a gas, a double arrow indicating the system is in equilibrium, C as a gas, and D as a liquid. This chemical equation is in equilibrium, meaning the system is dynamically moving in both directions at one time. So the forward reaction and reverse reaction are both moving in two directions at one time. The forward reaction rate equals the reverse reaction rate, and the concentration of reactants and products remains constant. A system will shift to the right or left in order to maintain equilibrium. If there is a shift to the left, this will increase the reactants and decrease the products. If there is a shift to the right, this will increase the products and decrease the reactants. Again, stressors that change the equilibrium are concentration, heat, and pressure and volume. Let's look at how concentration affects the chemical equilibrium first. If we increase the concentration of B, will the system shift to the left or to the right? It will shift to the right. It does this because there's an increase of reactants. Then the system needs to produce more product in order to balance out. And shift in the direction of the product will create more product. So there will be an increase in product and decrease in reactants. What if we decrease B? Will the system shift to the left or to the right? The system will shift to the left. Because there was less B reactant, the system shifted in the direction of the reactant to make more. A shift to the left increases the reactant and decreases the product. What if we increase C? Will the system shift to the left or to the right? The system will shift to the left. This will increase the reactant and decrease the product. And now what if we decrease the concentration of C? Will it shift to the left or the right? The system will shift to the right. This increases the product and decreases the reactant. Remember, Le Chatelier's principle is all about balancing both sides of the chemical equation. And that's all we're doing here. Also, remember whatever side needs to be increased will be the side the arrow will point towards. And that is where the shift will go. It will shift to the right if product needs to be increased, or it will shift to the left if reactant needs to be increased. What about if we increase and decrease the concentration of A? Well, A is a solid, and solids have no effect on the equilibrium shifting, so the concentration of A going up or down will have no effect. Now, the same goes for D. D is a liquid, and liquids also have no effect on the equilibrium. So if we increase or decrease the concentration of D, it will have no effect on the equilibrium. Basically, only gases will have an effect on the equilibrium. We know now how concentration has an effect on equilibrium. Let's see how heat affects equilibrium. Before evaluating the equilibrium shifts, we must first understand the difference between endothermic and exothermic reactions. In an endothermic reaction, energy is used or absorbed by the reactant in order to make the product. Because the reactants are using heat, you sometimes will see the heat written with the reactants or on the reactant side. On the contrary, in exothermic reactions, energy is given off or released by the reactants to create the product. So you may see heat written on the product side because heat is being released on this side. If heat is added to an exothermic reaction, the system will shift to the left. And if heat is added to an endothermic reaction, the system will shift to the right. It is important that you are able to identify an exothermic and endothermic reaction before determining which way the system will shift. Let's look at an example using this generic chemical equation. So here we have heat written on the reactant side, and that tells us that this is a endothermic reaction, right? If we increase the heat of this endothermic reaction, will the system shift to the right or the left? It will shift to the right. And if we decrease the heat of this endothermic reaction, will it shift to the left or the right? It will shift to the left. Okay, let's compare this endothermic reaction to an exothermic reaction. We have heat on the product side, which means this is exothermic. It's a hint that it's exothermic, right? If we increase the heat here, will the system shift to the right or to the left? It will shift to the left. And if we decrease the heat, which way will the system shift? It will shift to the right. If this is still confusing you, take some time to stop the video and look at the patterns here. Again, remember this rule. If heat is added to exothermic, there will be a shift to the left. And of course, if heat is decreased on an exothermic, the system will shift the opposite direction, so to the right. And for endothermic reactions, it's also opposite. If heat is added, the system will shift to the right. And if we do the opposite, meaning we decrease the heat, the system will move to the left. Okay, next let's look at how pressure and volume change the equilibrium. First off, let's make sure we understand how pressure and volume are correlated. This illustration shows atoms in a cup and a plunger on them controlling the volume and pressure. Pulling up on the plunger increases the volume and decreases the pressure. In contrast, pushing the plunger downwards decreases the volume and increases the pressure. So remember, increased volume equals decreased pressure, and decreased volume is equal to increased pressure. Changes in pressure are only significant if gases are present in the system. If pressure is increased, the system will shift to the side with the least moles of gas. And if pressure is decreased, the system will shift to the side with a greater amount of moles of gas. So let's look at an example. If we increase the pressure here, will the system shift to the right or to the left? An increase in pressure will shift the system to the side with less gas. So first let's count the moles of gas on both sides. On the reactant side we have 1 mole of gas, and on the product side we have 2 moles of gas. Since we have less gas on the reactant side, the system will shift towards the reactants. It will shift to the left. Now what if we decrease the pressure? Will the system shift to the right or to the left? If we decrease the pressure in a system, the system will shift in the direction of more moles of gas. So our system will shift to the right. Okay, let's sum up what we have learned. When we say a system is at equilibrium, it means the system is dynamically moving in both directions at one time. The forward reaction rate is equal to the reverse reaction rate, and the concentration of reactants and products remains constant. The stressors that perturb equilibrium, in other words, they have the ability to change equilibrium, are the concentration of the reactant and product, heat, and pressure/volume. Also, remember Le Chatelier's principle and how it relates to equilibrium. The principle states that if an external stress is applied to a system at equilibrium, the system will reestablish in order to maintain that equilibrium. Alrighty, moving on to our next topic, reaction rates. Reaction rate is the change in concentration of reactants and products over time. For a chemical reaction to take place, molecules must collide with each other with enough force greater than the activation energy, and they must collide at the correct place on the molecule. This area is called the reactive site. Let's break this sentence up a bit more. The activation energy is referring to the minimum amount of energy needed to start a chemical reaction. When two molecules collide, they must have enough energy to overcome the minimum activation energy. And the lower the activation energy, the faster a reaction can act. The higher the activation energy, the slower a reaction will act. The reactive site is referring to the specific area where the molecule needs to collide, or else it won't be able to break or bond. These two terms are often confused with each other, so remember, activation energy has to do with energy needed for the molecules, and the reactive site has to do with the site, obviously, an area on the molecule that is pretty much like a sweet spot for a chemical reaction to take place. Factors that affect the reaction rate are temperature, concentration, surface area, and catalyst. Increasing temperature will increase the reaction rate. Increased temperature makes molecules move faster. This increases the kinetic energy they have when colliding with each other, thus increasing the chance that sufficient energy will be transferred during the collision. Increasing temperature also increases the number of collisions because the molecules are moving faster. Increasing the concentration of the reactants or pressure if gases are involved increases the reaction rate. This is due to the fact that there are more molecules to collide with and react with. Increasing surface area of a solid, normally done by crushing a substance or cutting it into multiple pieces, allows for more space on the substance to interact with collisions. Lastly, adding a catalyst to the reactant will speed up the reaction rate. It does this by lowering the activation energy needed to create a chemical reaction. Let's emphasize a bit more on the catalyst. Adding a catalyst to the reactions will speed up the reaction rate. It does this by lowering the activation energy needed to create a chemical reaction. Let's look at a visual of this concept. We have time increasing as we go left to right on the x-axis and energy increasing as we go up the y-axis. The blue line represents a system, a chemical equation. On the left, we have the reactants, and on the right, we end with the products. At the peak of the line is the transition state. The area from the beginning of the reactants to the transition state is the activation energy. The blue line represents our uncatalyzed reaction, meaning there is no catalyst present. And our pink line will represent our catalyzed reaction, meaning there is a catalyst present. Notice the pink catalyzed reaction has a lower activation energy, meaning it will take the reactant less time to reach the transitional state and become products. That is how a catalyst speeds up a chemical reaction. It does so by lowering the activation energy. Other important things to remember about catalysts are that they can be used without being consumed, meaning they are reusable. Also, biological catalysts are called enzymes. So let's do a quick comparison of both topics we just went over, equilibrium and reaction rate. Equilibrium relates to balance in the system, how the concentrations of products and reactants in the system are balanced, and the rates forward and reverse reaction are also balanced. Reaction rate relates to speed, the rate at which the forward and reverse reaction are in. The connection between the two is that at equilibrium, the reaction rates are equal to each other. Before we go over some practice problems, I just want to show you this chart I developed. It's not super thorough, but it's sort of a shortcut reference if you're still getting the hang of it. You can screenshot it and use it on the side to look at while you're doing your practice problems. Also, just a warning, do not try and memorize the chart and bypass understanding the whole concepts because you will get very lost. This is just a supplemental chart. Also, keep in mind, I didn't write the opposites of each other. So, for example, I'm assuming you should understand that if we decrease the temperature for endothermic, it will shift to the left, and for exothermic, it will shift to the right, and so on. Okay, so let's get into these practice problems. All of these are straight from the official ATI TEAS 7 study manual. I thought I'd go over them so you can get used to the wording because honestly, the wording ATI uses is honestly a little funny and different. So, starting with question number 1. Equilibrium would favor the reactant side if which of the following occur? By the way, when you see the word favor, it means shift towards, okay? So shift towards. So this means equilibrium would shift towards the reactant side if which of the following occurred. So A, if H2O is added. H2O is a product here. If we add product, the system will shift towards the reactant in order to balance it out. Or we can say the system will favor the reactant side. Same thing. So this is our answer here. This is our correct answer. B, if we decrease the temperature, well, we know this is an exothermic reaction, right? Because we see the heat on the product side. So remember our rules for exothermic reactions. If we increase the heat, it will shift to the left. If we decrease the heat, it will shift to the right. So here, temperature is decreased on an exothermic reaction. So the shift will be towards the products. So that makes this B wrong. Next, if carbon monoxide is added. Well, carbon monoxide is a reactant. So increasing our reactant will cause the system to shift to the product side. And if we remove methane, methane is from the product side. The system will shift towards the product side in order to compromise. So all of these are wrong and our answer A, H2O, is right. Awesome. So next question. A substance that lowers the activation energy is which of the following? Our answer here is catalyst. So this question comes up a lot on the practice questions. Make sure you know exactly what a catalyst does and what it's used for and how it relates to reaction rates. Alrighty, next question. Which of the following would increase the forward rate of the gas phase reaction? Okay, so first, I just want to point out that the forward rate is going this way, from the reactant to the products. So the question is only referring to increasing the rate in that direction, from left to right. A, if we add a carbon monoxide to the reactant side, this will definitely increase the rate of the reaction because increasing the concentration of reactant will increase the forward reaction rate. B, increasing the temperature. First off, we have an exothermic reaction. If we increase the heat on an exothermic reaction, the forward rate slows down and the reverse rate speeds up. So this does not increase the forward rate, it slows it down. How about adding H2O? H2O is adding more product, so the system will shift towards the reactants. This increases the speed going towards the reactants, but it decreases the speed going towards the products, that being the forward rate. So here the forward rate slows down. Lastly, increasing the pressure. Increasing pressure equals increasing heat. As you increase the pressure, you're also going to increase the heat in a system. So this is exactly what happens in answer B scenario. The increase in heat on an exothermic reaction will decrease the rate of the forward reaction. Alrighty everyone, that's it for this video. If you're looking for more practice problems, I'll be uploading some this month, and also I'll be adding a few to my Instagram this week. Just check on my stories. There'll be practice problems on chemical equilibrium and reaction rates. Alrighty, thanks so much for sticking around. I hope you learned something new, and until next time.